Hello everyone. Today we are going to present our work MEC, Mask Augmentation for Motion-Aware Video Representation Learning. This is a collaboration work with Ufuk Umut Şentürk and Nazlı İkizler Cimbiş. Our study explores novel ways for learning video representations in a self-supervised manner. Before getting into details of the proposed method, our study depends on two critical observations. Firstly, background bias is inevitable when learning from videos, because CNNs have the tendency to find shortcuts. In a previous work, when learning from multiple frames, only one frame was shown to be sufficient to predict correct action class. CNN was responding to a single frame without learning the action dynamics. Additionally, background bias is strongly related to data we use for learning representations. The way we collect datasets result in certain bias towards semantics. Previous works have shown that even the actor or the moving foreground is masked out. Trained models were capable of predicting correct classes due to strong scene and object bias in the background. And our second observation is that video representation learning is one of the areas that could benefit most from self-supervised learning paradigm. While videos are difficult to annotate, self-supervision removes the dependence on ground truth. And when applied properly, we believe it has the potential to extract more generalizable features because there is no direct supervision for models to memorize. Since our motivation is to learn based on foreground motion, capturing the spatial temporal dynamics of foreground is beyond limits of supervised learning. So we basically approach self-supervised video representation learning from two directions. We introduce a novel augmentation technique MEC. The idea is to focus more on the motion in the foreground. We believe this approach is particularly useful for motion-related downstream tasks such as action recognition, since learning mainly depends on motion features. Another benefit is that learning from motion potentially prevents possible shortcut learning from background. Our proposed augmentation technique is cheap to compute, depending on basic frame differences. As can be seen from sample gradcams, when learned from raw RGB frames, focus is scattered over the whole scene. On the other hand, our MEC makes it possible for model to focus mainly on the motion. Our second approach is to introduce two novel learning objectives that utilize MEC augmentation. The first objective is based on turning a prediction game into a self-supervised pretext task. The basic idea is to apply MEC on video clips and predict the applied transformation as a classification task. And the second objective is a form of contrastive learning in which we apply MEC on query samples together with other standard augmentations. These augmentations include standard resize and random cropping, grayscaling, and color jitter. We also sample frames from videos with varying temporal stride to account for various temporal versions of the action. It must be noted that MEC and other standard augmentations prevent network from reverse engineering pixel-level details to easily solve prediction tasks. Otherwise, the generative learning would result in learning representations that won't generalize well to downstream tasks. Here is the general MEC framework. As a processing step, we have mask augmentation. After mask extraction, we apply a blending operation to combine manipulated foreground with background. Note that the multiplier parameter used to manipulate foreground is also utilized as pseudo-ground truth in self-supervised loss. Lastly, we have self-supervised and contrastive losses to pre-train our models cooperatively. So, how our method works in details? Firstly, our mask extraction technique has cheap computation requirements and computed for each frame. Our extraction technique composes of simple frame differences with a momentum structure that models background as a weighted sum of previous frames. After extracting foreground masks for each frame, we perform a blending operation that completes our augmentation technique MEC. We multiply all the foreground regions with a multiplier alpha, and we keep the background regions untouched. Then we blend foreground and background parts to achieve a manipulated version of original frame. Lastly, We train our models with our two objectives that are previously mentioned. Both objectives utilize MAC in different ways. Our SSL objective uses a cross-entropy loss to predict correct multiplier alpha. Our motivation with this objective is that in order to successfully predict the correct multiplier, any network is constrained to embed motion-related features. In other words, we teach the network to always follow the motion without directly dictating it, but just via a transformation-based pretext task. Our contrastive framework utilizes usual info-NC loss to optimize positive pairs, query and key together, and push negative pairs aside. As mentioned earlier, MAC is applied only on query that results in a manipulation from key sample. Since the manipulated bits between Q and K is the moving parts, we believe the only relation to take positive samples together is to embed motion features. We performed experiments to validate the effectiveness of our method and understand the impact of each module. To begin with, we wanted to understand the effect of each objective. We trained models with only SSL objective, with only contrastive objective, and used them cooperatively. As a baseline, we trained a model with info-NC loss, but using only standard augmentations. As can be seen, both SSL and contrastive models are superior against contrastive baseline. It is also remarkable that combining both objectives is even superior. That demonstrates that both objectives are working cooperatively and complementary. Here we also present results for using different number of multipliers. 2 means input clip is split into 2 subclips, and different multipliers are sampled and predicted for each subclip. As seen, increasing the number of multipliers and number of subclips would increase the accuracy of models. We believe model is constrained to predict a more complex classification problem and has to embed each subclip separately to correctly predict. That in return increases the temporal variance. Here we present action recognition comparison to the recent state-of-the-art methods for UCF 101 and HMDB 51 datasets. In similar settings, our work stays on par with state-of-the-art transrank method that is also based on transformation recognition paradigm. It is remarkable that our simple method with cheap computation requirements falls not far from large-scale methods like ROBIOL, Brave, and CVRL that have large backbones with more pre-training epochs and higher resolution inputs. Although UCF, HMDB, and Kinetics are common datasets, we also provide results for Diving 48 dataset that is known to be less biased. We achieve superior results for Diving 48 since our learning paradigm aims to remove reliance on background and scene elements. Our retrieval results is compared to recent methods that have similar computation setups. We provide successful results for both UCF 101 and HMDB 51 datasets. In order to understand whether our learning really depends mostly on motion, we designed a setup to compare with a MoCo V2 model and a supervised K400 pre-trained model. We created a new version of UCF 101 as still UCF by using only 1/3 of each video to decrease the temporal variance and sample only 4 frames and use each of them 4 times repetitively. Obviously, still UCF is a more static dataset than usual UCF, and we fine-tune these 3 models on both UCF and still UCF. Consequently, action recognition performance of both MoCo V2 and supervised K400 models decreases around 2 to 5%, while our model's performance decreased nearly 14%. That simply shows that our learning heavily depends on motion features. Finally, we show a few video samples with raw frames and gradcams of a supervised model pre-trained on K400 and our model and the corresponding computed masks. It can be observed that MEC is more robust to focus on motion and foreground than supervised model. We believe both qualitative and quantitatively MEC is a simple but effective augmentation technique that drives models to focus on motion and foreground. Finally, to conclude this study, we presented a mask augmentation technique that is simple but effective. We propose two ways of utilizing MEC as a learning objective. SSL objective that forces model to attend on motion, and contrastive objective to use motion as a similarity metric between positive pairs. From experimental results and qualitative observations, we demonstrate that our learning paradigm heavily depends on motion features with background invariance. Thank you for joining us today.